You see, let me try that again. You see, before we step into the vastness of it all, let me ask you something. Something simple, yet strangely heavy. Have you ever looked up at the night sky and wondered whether light itself might be too slow? Because it's strange. It's strange how that question lingers, isn't it? I suppose it's a curious thought, and, it's one that keeps returning to me. Because out there, across the great dark ocean of the Milky Way, even a beam of light, this cosmic racer that's been sprinting since the dawn of time, would need tens of thousands of years just to cross our own galactic home. And that number, well, it settles into your mind like fine cosmic dust. It makes you feel the quiet weight of distance, the almost unbearable scale of the universe we inhabit. So I find myself wondering again, and maybe you do too. Are we truly imprisoned by space and time? Or is there, hidden somewhere in the equations, well, somewhere in that delicate stitching of space-time, a loophole, a wrinkle, a possibility that might let us slip past the cosmic speed limit itself? And, well, tonight, you and I will wander through that question together. Gently, slowly, as if drifting through a corridor of starlight. And the ideas, they echo softly, and the possibilities glow faintly at the edges. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And, since we're sharing this little journey through the cosmos together, tell me, where are you listening from tonight? I suppose I always love knowing where on this pale blue dot you're tuning in. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, you see, when we talk about the speed of light, we often imagine it as just another number, just another limit the universe casually throws in our path. But, it is not just a number. It is a boundary woven deep into the fabric of reality itself. And as we look out into the night sky, that dark and glittering ocean of stars, we find ourselves asking the simplest yet most unsettling question. Why can nothing outrun light? Why does the cosmos insist on this rule, as if guarding some ancient secret? Einstein, back in the early years of the 20th century, in that remarkable year of 1905, proposed something that, well, forever altered the way we understand motion. He suggested that space and time are not independent actors drifting lazily beside each other. They are one thing, a single stage on which every event, every particle, every memory unfolds. And the speed of light is not just fast, it is the maximum speed at which information, cause, and effect can ripple across that stage. But the deeper you look, the stranger it becomes. When an object with mass begins to accelerate, it resists. Not just in the usual way we imagine weight resisting being pushed, but in a subtler sense, its inertia grows. And, well, the faster it moves, the more stubborn that inertia becomes, as if the universe is gently holding it back, whispering that there are places it simply cannot go. At everyday speeds, this resistance is tiny, ignorable. But as you approach a significant fraction of the speed of light, that resistance balloons. Energy pours in, and yet the velocity creeps forward ever more reluctantly. It becomes clear that to reach light speed itself would require not just great energy, not just unimaginable energy, but infinite energy. And infinity, in physics as in life, is a barrier that no amount of clever engineering or wishful thinking can overcome. Perhaps the universe does not allow anything with mass to reach the cosmic speed limit because mass distorts space-time, creating its own little indentation in the cosmic fabric. And light? Light is different. It is pure energy. It is the only thing that can surf that fabric without disturbing it. So we find ourselves in this curious situation. Light plays by rules we cannot break, yet we are forever trying to chase after it, as though trying to catch a shadow cast by creation itself. And when you test these ideas in laboratories, the story becomes even more compelling. In particle accelerators, where protons or electrons are hurled around rings at energies that make the entire facility hum, the particles reach speeds so close to the speed of light that the remaining difference is unimaginably tiny. But no matter how much energy scientists add, no matter how hard they push, the velocity refuses to cross that final threshold. Instead, the particles grow heavier. In a sense, or rather their inertia grows. It is not weight in the everyday sense, but a kind of energetic burden. The faster they go, the more the energy pours not into speed, but into mass. The machine is telling us, again and again, that Einstein was right. We see the same effect in the ticking of atomic clocks flown on aircraft or placed in satellites. Time itself slows at high speeds. It is not a metaphor. It is not a poetic flourish. It is measurable. GPS satellites orbiting thousands of miles above Earth carry clocks that tick ever so slightly differently from clocks on the ground. And, if those differences were not corrected constantly, the entire system would drift, and our maps, our navigation, our sense of place in the world would fall apart. So it becomes impossible to dismiss relativity as abstract theory. It is something we depend on every day, whether we realize it or not. You might think, well, perhaps we could cheat. Perhaps there is a loophole. But no matter which angle we approach it from, the same answer returns. Nothing with mass can be accelerated to the speed of light. Not just because we lack the technology, but because the universe is built that way. It is not an engineering problem. It is a structural one. And, this reveals something quietly profound. The universe is not a playground for our imagination alone. It is a place with rules, limitations, and boundaries that shape everything from particle physics to the lifespan of stars. Those boundaries give the cosmos its texture, its consistency, even its beauty. For if light were not limited, if causality could be broken, if information could leap across spacetime instantly, the universe would lose its coherence. It would be chaos, without pattern or predictability. So, in a sense, the cosmic speed limit is the universe keeping itself intact. It is the quiet law that lets galaxies form, stars shine, and life emerge on a small blue world orbiting a quiet yellow sun. It is not a cage, it is a foundation. But I suppose the most striking aspect of all this is philosophical. When we stare up at the night sky, the stars we see are old. Their light has traveled years, centuries, millennia to reach us. It carries memories of distant places and long-gone moments. And maybe, perhaps, the reason we cannot outrun that light is that the universe is inviting us to slow down, to listen, to reflect. The cosmos is not a race, but a story, unfolding one photon at a time. And yet, despite this beautifully intricate limit, humanity remains restless. We ask whether there is some trick of geometry, some warp in the fabric, some way to bend space so that we do not outrun light, but instead reshape the path beneath us. It is not that we want to break the law. It is that we want to understand it so deeply that perhaps, we could move around it, the way a river bends around a rock. That is the heart of scientific curiosity, not rebellion, but exploration. As we look deeper into Einstein's equations, we realize they are not forbidding. They are revealing. They tell us that space and time can stretch, compress, and twist. They tell us that gravity is not a force in the ordinary sense, but geometry. And if geometry can be shaped, then perhaps, just perhaps, there are ways to travel great cosmic distances without ever breaking the sacred speed limit. But before we leap into such exotic dreams, we must first understand the scope of the problem. Because the universe, well, it is vast in a way that defies intuition. Even at the speed of light, traversing it would take tens of thousands of years. And with our current technology, moving even a fraction of that speed feels impossible. We are confined, for now, to our little corner of the cosmos. So the question lingers in the air. If light defines the ultimate limit, and if nothing with mass can reach or exceed it, how can humanity ever hope to touch those distant worlds? And, if the speed of light is the universe's way of preserving causality, what happens if we find a way to work with spacetime rather than against it? This is where our journey begins to shift. The boundary of light is not the end of the story, but the first threshold. Understanding why we cannot move faster allows us to see the true shape of the challenge ahead. And even though Einstein's equations set firm constraints, they also, quietly, offer hints of astonishing possibilities hidden in the deep structure of spacetime. And so, as we stand here, on this small world in the year 2025, gazing outward across the interstellar gulf, the real question is not simply why the speed of light is a limit. The deeper question, the one that carries us forward, is this: if the cosmos is so astonishingly wide, why is light not enough? And what does that mean for the journeys we dream of taking? And that, well, that leads us naturally to the next part of our exploration, where the scale of the universe itself begins to reveal just how small and slow we truly are, and why the dream of reaching other stars demands something far beyond ordinary motion. And so, as we left off with that lingering question about why the speed of light is not enough, we begin to feel the immensity of the challenge before us. The cosmos, well, the cosmos is not merely large. It is vast in a way that bends the mind, that stretches the imagination until it trembles. And the more you look out there, the more you realize that the speed of light, impressive as it sounds, is painfully slow when measured against the scale of the universe. You see, when we talk of distances, we often think in miles or kilometers, in units that describe the roads we've walked or the flights we've taken. But out there, those measures crumble. Distances slip beyond the reach of intuition. So, scientists turn to something else. They use light itself as a ruler. 1 year of travel at the fastest speed possible becomes a single mark on the cosmic map, a light year. And the nearest star, Proxima Centauri, sits a little over 4 of those marks away. 4.2 light years. It sounds modest at first, like a short stroll across the cosmic neighborhood. But then you try to imagine what that means. Light, moving at nearly 300,000 kilometers every single second, needs more than 4 years to get there. And, our fastest spacecraft, well, they crawl by comparison. Take the Parker Solar Probe, racing around the sun at extraordinary speeds, faster than any human-made object has ever flown. Even then, even at its astonishing peak velocity, it would require thousands of years to reach that first faint ember of another solar system. And Voyager 1, that silent explorer drifting far beyond the planets, continues its lonely journey outward. But if you measure its progress against the stars, it barely moves at all. a slow dance on the edge of darkness. So the question emerges again, repeating like a gentle echo. If our nearest neighbor is already so distant, what hope do we have of reaching the worlds that truly stir our imaginations? Because just a little farther out, across that same night sky, lies the TRAPPIST system. 7 planets orbiting a tiny star, a compact family of worlds where at least 3 lie in the habitable zone. And yet, it sits nearly 39 light-years away, not just beyond reach, but beyond any travel method we currently understand. And if you lift your eyes even higher to the dreams of an Earth twin, a world like ours orbiting a star like ours, then you may find Kepler 452b, a beautiful possibility, a whisper of familiarity in the void. But that world lies more than 1,400 light-years away. So far that the light we see left during a time when humanity had not yet begun to map the world, when we were still learning how to tell stories by firelight. And, if we were to dispatch a craft today, even at a considerable fraction of light speed, it would arrive long after every civilization we know has risen and fallen. So, we begin to feel something humbling, almost spiritual. It is not just that the universe is big, it is that we are small. Our machines, our engines, our rockets, they are remarkable achievements of intelligence and persistence. But when compared to the cosmos, they are like seeds thrown into a vast and restless ocean. And yet, we keep looking outward. Because that is who we are. We grow older, clocks tick, stars drift, and still we search. It's not just ambition, it's curiosity. A quiet longing to understand whether life exists elsewhere, whether the stories that unfold on distant worlds echo our own. And perhaps even the desire to become a multi-planet species, not just for survival, but for wonder. But to even imagine such journeys, we must confront a truth that feels almost paradoxical. Light, the fastest thing in existence, is too slow for the dreams of humankind. And it is this mismatch between the scale of our hopes and the scale of the universe that shapes the greatest engineering and scientific challenge of our age. When you look at spacecraft speeds plotted beside the distances they must cross, the picture becomes almost absurd. The fastest rocket humans have ever built cannot complete even 1% of the journey between stars within the span of a human lifetime. We could launch generations of ships, entire families living and dying inside steel habitats drifting through the void, and still struggle to reach even the nearest star. It's not a matter of difficulty, it's a matter of scale. And, well, this is why scientists often say, not with despair but with clarity, that if we truly intend to explore other planetary systems, we need something fundamentally different. Not just better fuels, not just bigger rockets, but a new kind of thinking about motion itself. Because the tyranny of distance is absolute. The universe is simply too large for conventional propulsion to ever be enough. And yet, there is something beautifully humbling in this. The night sky becomes a reminder of our place in a story far larger than ourselves. Every photon reaching our eyes tonight carries the weight of time, the memory of its star, the imprint of its journey. And that reminds us that travel across such enormous distances is not trivial. It requires patience. It requires imagination. Perhaps even a redefinition of what we mean by a journey. But when we talk about scale, we should consider more than distance. We should consider time. For example, the light from Kepler 452b takes over a millennium to arrive here. So it shows us the world as it was, not as it is. And by the time any signal from us reaches there, and any signal returns, countless generations will have lived entire lives. In a sense, interstellar conversations become correspondences written across epochs rather than moments. It becomes a kind of cosmic archaeology. The universe, in this way, forces us to think not just outward, but forward. And, as we do, we must confront a quiet but profound truth. If humanity is to reach another star system, we must learn to move not through space, but with it. Because crossing space at sublight speeds is like trying to swim across an ocean with hands alone. It's noble, it's courageous, but it will not get you to the far shore. So, scientists point again and again to the same conclusion. The distances are too great, the speed limit is too strict, and the dreams we hold require us to imagine something new, something that sidesteps the old ways of thinking, something that perhaps uses geometry rather than thrust, spacetime rather than fuel. But before we come to those ideas that belong to warp drives and exotic geometries, we must fully appreciate the scale of what we are facing, because the more you understand the size of the universe, the more those radical ideas begin to feel not like fantasy, but like necessity. And, as you imagine spacecraft drifting through the void, their engines pushing feebly against the immensity of the cosmos, you may realize just how fragile our current methods are. Rockets rely on pushing mass out the back to move forward. But at interstellar distances, even the most efficient designs falter. The fuel required becomes unimaginable. The physics itself becomes a cage. And that is why the cosmic distances matter. They do not just shape our engineering. They shape our philosophy. They shape our understanding of what it means to travel, to explore, to seek. It becomes clear that reaching other stars is more than a technical problem. It is a conceptual one. And perhaps this is why the scale of the universe calls to us with such force. It reminds us that the cosmos is not built to be easy. It is built to be vast, mysterious, almost impossibly grand. And in that vastness, we find meaning. We find humility. We find the deep and curious truth that exploration is not guaranteed. It must be earned. But if we are to earn it, if we are to reach the worlds we dream of, then we must first face the limitations of the technology we have relied on for a century. We must look directly at the rockets that carried us to orbit, to the moon, to the outer planets, and accept that they will never carry us to the stars. And, as the Parker Solar Probe dives ever closer to the Sun, and as Voyager 1 drifts into the interstellar medium, we see both triumph and boundary. Triumph in human ingenuity, boundary in cosmic scale. The gulf is enormous, and no amount of conventional thrust can bridge it. So the thought arrives again, not as a complaint, but as a quiet realization. To cross the stars, we must think differently. Not bigger rockets, but new physics. Not brute force, but elegance. And with that understanding, the next question begins to form in the mind, almost hesitantly. If rockets cannot take us there, what can? If the universe is so vast that even light is too slow, what kind of journey remains possible? And, those questions, fragile and bold at once, lead us directly into the next great challenge: the fundamental limitations of rockets themselves, and why even our most ambitious propulsion systems fail to break free of the cosmic scale that surrounds us. And, as we follow that thought into the heart of the problem, we arrive at the uncomfortable truth that our rockets, remarkable as they are, carry within them a quiet and stubborn limitation. It is a limitation woven not into engineering, but into physics itself. And well, the more we look at these engines that have lifted us from Earth and carried our instruments to the planets, the more evident it becomes that they simply cannot, take us to the stars. You see, rockets work by pushing mass out the back. The faster you want to go, the more mass you must throw away. And the more mass you throw away, the heavier the rocket becomes at the beginning of its journey. So, you add more fuel to compensate, and that fuel itself has mass, and then you need even more fuel to push that mass, and suddenly you enter a kind of endless spiral, a trap hidden inside the mathematics, the rocket equation, a tyranny of exponentials. The faster you wish to travel, the more impossible the task becomes. It's not just engineering, it's not stubbornness, it's physics whispering that there is no free lunch. Every action demands a reaction. Every push demands something to push against, and the rocket must carry all its pushing material on board. That is the heart of the problem. When we think of a long journey, say to Mars or to the outer planets, the rocket equation feels manageable. Difficult, yes, but manageable. But stretch that journey to Proxima Centauri or to the Trappist worlds, and the equation becomes monstrous. The amount of fuel required grows so quickly that no material, no structure, no technology we can realistically imagine could contain it. And, if we try to imagine a rocket accelerating to even a tenth of light speed, the speed scientists often point to as a dream threshold for interstellar travel, we hit a wall. 1/10 of the speed of light is still unimaginably fast by human standards. Yet the energy required to push even a lightweight craft to that velocity surpasses anything our civilization has ever generated. It becomes clear that rockets are perfect for planetary travel, for exploration within a solar system, but they are utterly inadequate for journeys between stars. And if we turn to alternatives, ion drives, nuclear rockets, fusion propulsion, we find elegance, creativity, and astonishing promise, but also ceilings we cannot break. Ion drives produce a steady, gentle push, but so gentle that they cannot accelerate a craft to meaningful fractions of the speed of light in any practical time frame. Nuclear rockets offer more thrust, but still fall short. Fusion reveals dazzling potential, the same engine that powers the stars themselves, but even then, the physics imposes limits. You might reach a few percent of light speed. Perhaps, but even that is optimistic. And once again, we find ourselves confronting the same unsettling truth. We cannot brute force our way across the universe. Not with rockets, not with conventional thrust, not with the engines we can build in the world we inhabit today. Well, perhaps a metaphor helps. Imagine standing at the shore of an ocean so vast that no boat, no matter how well built, can cross it before lifetimes pass. That is where we find ourselves. Earth is the shore. The stars are across the water, and our rockets are boats carved from wood. Majestic, ingenious, but hopelessly outmatched by the size of the sea. And yet, there is something beautiful in this, something deeply human. Because even as the universe reveals our limitations, we keep searching, we keep pushing, we keep dreaming. And, in that struggle, there is meaning. But let's look more closely, because the deeper you examine the rocket equation, the more its tyranny becomes almost poetic. Every bit of fuel you add to go faster requires more fuel to push that fuel, which requires more fuel still. It's a self-consuming loop. So, if you want to go twice as fast, you don't need twice as much fuel. you might need hundreds or thousands of times more. The numbers explode. And this explosion of requirements is why rockets simply cannot reach even a moderate fraction of light speed. They can accelerate quickly, yes. They can escape planets. They can cruise across the solar system. But they cannot carry the monumental amount of energy required to push themselves into the realm where interstellar distances become navigable. It's not a failure of imagination. It's a reminder of scale. The universe is not sized for rockets. And think of momentum itself, the simple idea we learn as children. If you want to go faster, push something backwards harder. But in space, there is nothing to push against except what you carry. And that turns a simple idea into a cosmic challenge. Momentum conservation becomes the very law that limits our reach. There is another way to see it. As a rocket accelerates, the fuel inside it is still inside its own frame of reference. The rocket must accelerate its own fuel along with its payload. So the faster it goes, the harder it becomes to accelerate the remaining mass. And by the time you approach even a small fraction of light speed, much of your energy is spent not on gaining speed, but on pushing the burden of your fuel itself. It's not just a technical problem, it's a conceptual one. We are trying to cross a galaxy using machines designed for the gentle, local architecture of a planetary system. And, well, the truth is this. The rocket equation is the universe gently reminding us that we need to think differently. It's telling us that propulsion based on expelling reaction mass has reached its useful limit. And this is why every proposal for interstellar travel acknowledges the same uncomfortable fact. Ion drives, nuclear pulse drives, fusion sailcraft. They all face ceilings far below the speeds needed to reach another star in a human lifetime. So, we come to a kind of crossroads. Our rockets can take us far, but not far enough. They let us skim the surface of the cosmic ocean, but never cross it. And that is why scientists, dreamers, and engineers have for decades explored alternatives. Solar sails, beamed propulsion, antimatter engines. Concepts that push at the edge of known physics. But even these face challenges. Solar sails need enormous distances to accelerate and cannot reach the required velocities without unimaginable power sources pushing from afar. Antimatter engines sound impressive, but antimatter itself is painfully rare and difficult to produce. And even if we had enough, the energy released would still be insufficient to move large spacecraft at significant fractions of light speed. And so the conclusion remains the same, repeating softly like a refrain. Rockets, in all their forms, are not the answer to interstellar travel. They cannot be. Their method, expelling mass, is fundamentally mismatched to the vastness of cosmic distances. Yet there is something almost comforting in facing this limit. Because once we accept that rockets cannot take us to the stars, we free ourselves to imagine something entirely new. Something not bound by the need to carry fuel. Something not imprisoned by the rocket equation. And it's here that the mind begins to wander into more radical possibilities. What if, instead of pushing ourselves through space, we let space itself move around us? What if velocity is not the path but the illusion, and the true key lies in geometry rather than thrust? What if the solution isn't found in engines burning hotter, but in the structure of space-time itself? And, that thought leads us naturally, inevitably, to Einstein again. Because the same theories that showed us the impossible limits of rockets also reveal something profound. Space-time isn't rigid. It can stretch. It can warp. It can bend. And if it can bend, well, perhaps it can be shaped into a pathway. That That is the beginning of an idea so bold it almost feels like fiction. Yet the mathematics exists. The theories exist. The whispers of possibility are real. But before we walk fully into that world of warped geometry, of bending space rather than crossing it, we must first understand how relativity itself shapes our perception of motion at high speeds, and why even traveling near the speed of light does not solve the problem in the way we might hope. And, as we follow that train of thought, we find ourselves stepping gently into the next realm of the story, into the strange and wondrous effects of relativity that emerge when we approach the cosmic speed limit. Effects that twist our notions of time and length in ways that challenge everything we think we know. And, as we step gently from the limits of rockets into the realm of motion itself, we find that the universe has one more set of rules waiting for us. Rules that emerge only when you approach extraordinary speeds. Rules that twist familiar ideas into shapes that feel almost dreamlike. Because once you begin moving close to the speed of light, the world you thought you knew begins to behave in ways that seem, well, almost magical. And yet every one of these effects is real, measurable, undeniable. It's here that Einstein, again, offers a kind of compass. His theory of relativity does not merely tell us that we cannot reach the speed of light. It tells us what happens when we try. And the things it reveals, time slowing, lengths shrinking, mass increasing, are not just abstract curiosities. They are deep, physical truths woven into the very structure of spacetime. So, perhaps the best way to understand them is not through equations, but through a story of what you would experience if you were one of the few daring souls who could ride a spacecraft accelerating toward that unreachable cosmic boundary. Well, imagine sitting inside that spacecraft. The engines ignite. You begin to accelerate. At first, everything feels normal. Seconds tick, your heartbeat steadies, and the stars drift lazily around you. But as your speed climbs, 10%, 20%, 30% of the speed of light, something begins to change. And the change isn't out there. It's in here, inside your perception, inside the flow of time, time dilation, the slowing of time itself. It's not metaphor. It's not illusion. It's something the universe does too, preserve the speed of light. As you travel faster, your internal clock, your heartbeat, your thoughts, the aging of every cell in your body, begins to slow relative to the world you left behind. And, well, if you could look back at Earth, you'd see clocks there ticking ever so slightly faster than yours. The faster you travel, the bigger the difference grows. And this effect, this bending of time, has been verified again and again. Muons in particle accelerators live longer when moving fast. Atomic clocks flown on jets tick differently from those on the ground. GPS satellites require relativistic corrections, or their navigation signals would drift disastrously. So, relativity is not a theory of abstraction. It is a theory that shapes the infrastructure of modern life. But out there, in the silent dark between stars, the consequences become astonishing. Suppose you accelerate to 90% of light speed, then to 95%, then 99%. Your perception of time could slow to half or a tenth of the rate back home. You might age only a few years, while Earth ages decades. And, in a way that is both beautiful and unsettling, this creates a paradox of experience. You might look out the window and feel as though your journey is manageable, perhaps even short. But the people waiting for you back home will perceive it very differently. Their clocks tick faster. Their centuries pass swiftly. You You're caught in a bubble of slow time. And yet, time dilation is only half the story. There is another effect, equally profound. Length contraction. As your speed increases, distances in the direction of motion shrink. Not because space itself collapses, but because spacetime rearranges itself so that events remain consistent for all observers. So from your perspective, the distance between you and Proxima Centauri begins to become smaller. At 99% of the speed of light, it might appear only a fraction of its normal length. This is one of the strangest and most beautiful consequences of relativity. The faster you move, the shorter the universe becomes. The stars seem to draw nearer, pulled toward you as though by some invisible gravitational tide. It's not just physics. It feels almost like poetry, written into the geometry of existence. But here is the twist. Even though distances contract for you, from Earth's perspective, the distance remains the same. And Earth's perspective is what matters when we measure true travel time across the cosmos. So even if your own journey feels brief, the universe outside still demands decades or centuries before your craft reaches another star. Not just because time behaves strangely, but because relativity protects the speed of light with an almost stubborn elegance. And, this leads us to an important realization. Relativity does not merely limit us, it warns us. It says, even if you could accelerate close to the speed of light, even if you lived in slow time with distances shrinking around you, the universe outside does not share your shortcut. From Earth's frame, you're still crawling through an ocean of space that refuses to yield. And the energy required to reach such speeds grows catastrophically. So even if the relativistic effects seem to help the traveler, they shrink distances, they slow time. They do not help the civilization waiting for news back home. So, this is why near light speed does not solve the problem of interstellar travel. It helps the traveler, but not the universe around them. Well, perhaps the most haunting aspect is the duality of it all. Time dilation softens the journey, but does not alter the distance. Length contraction offers an illusion of progress, but does not change the energy required. It's not that relativity betrays us, it's that relativity is honest. The cosmos is consistent. And consistency, strangely enough, is what makes the universe stable. But let's travel a little deeper into the experience. Imagine you have somehow built a vessel, something sleek, something impossibly strong, that accelerates to 99.9% of the speed of light. Your time slows dramatically. Perhaps one day aboard your craft matches years back on Earth. You are suspended in a peculiar river of time where your own flow nearly halts. And the, strange thing is that for you, the journey feels short. But for Earth, for the people you love, for every consciousness bound to the slower frame, entire generations may rise and fall before your arrival. It's not just physics, it's heartbreak written across space-time. And, well, in a way, relativity reveals something larger. That high-speed travel does not merely challenge engineering, it challenges meaning itself. Because any journey you undertake at such extreme velocities will separate you from your own history, from your civilization, from the world that launched you. Time dilation becomes a barrier not of distance, but of relationship. You return not as a traveler, but as a relic from another era. We grow older, clocks tick, but not together. And so, even though relativity seems to offer a path, shorter distances for the traveler, longer life for unstable particles, the possibility of reaching distant stars within a single human lifetime, it also imposes a cost that cannot be avoided or engineered away. To move at such speed, is to sever yourself from the timeline of your origin. And if we reflect on this, quietly, perhaps with a sense of melancholy, we begin to see that relativity is not merely a barrier. It is an invitation to rethink what travel even means. If crossing great cosmic distances distorts time itself, then perhaps the solution to interstellar travel does not lie in moving faster, but in moving differently. And, as we consider this, the universe presents its final lesson on relativity. Even if you could move near the speed of light, the journey to distant stars would still take decades or centuries from the viewpoint of home. And for large craft carrying humans, the energy requirements are beyond anything we can generate. Not just vast, not just immense, but orders of magnitude beyond the reach of any foreseeable technology. So, relativity beautifully reveals the shape of the challenge. It tells us that high speeds warp time and space in extraordinary ways. It shows us the wonders and the paradoxes. But it also whispers that none of these effects free us from the cosmic scale that cages our rockets. And perhaps this is where another thought begins to form. A thought that lingers, tentative, but persistent. If moving through space is so energy demanding, so time distorting, so constrained by relativity, then maybe the answer is to ask a different question. Maybe it's not about traveling faster within space-time. Maybe it's about reshaping space-time around us. Because relativity, for all its limits, also contains within it the seed of something astonishing. The equations that prevent us from surpassing the speed of light also hint that space itself can stretch faster than light. That the universe expanded in its earliest moments in a way that outran even photons. That geometry, not speed, is the true architect of cosmic motion. And, that idea opens a doorway. A doorway not to breaking the laws of physics, but to bending them in ways that allow us to travel without moving in the conventional sense. A doorway toward a concept that sounds like science fiction, yet arises directly from Einstein's own equations. And so, as we carry these strange and beautiful truths forward, time slowing, space shrinking, clocks drifting, we find ourselves stepping toward a new and radical possibility. A possibility that does not fight relativity, but embraces it. A possibility where the key is not to outrun light, but to make light's limit irrelevant by shaping the very fabric it moves through. And, that is where our journey naturally leads next, into the bold and almost unbelievable idea that perhaps, instead of forcing our ships through space, we could persuade space itself to carry us, to move around us, to become the engine of our voyage. And, as we drift from the strange beauty of relativity and its quiet reshaping of time itself, a new thought begins to form, tentative, shimmering at the edge of imagination. Because if the universe refuses to let us move through space fast enough, then perhaps the only thing left is to ask whether space itself might be persuaded to move around us. And this is where the story takes a bold turn. It's not just a shift in engineering. It's not just a change in ambition. It is a shift in worldview. A recognition that space is not a passive stage upon which events unfold, but an active participant in the cosmic drama. We have grown up thinking of space as emptiness, as a void, as the nothing between stars. But according to Einstein, it's not nothing. It's a fabric, flexible, malleable, dynamic. And if it can stretch during the birth of the universe, if it can ripple as gravitational waves, then perhaps it can be bent, shaped, molded. So, imagine something almost paradoxical. Imagine a starship that does not move through space at all. Instead, the space behind it stretches outward while the space in front of it contracts inward, and the ship itself simply rides the curvature, floating inside a pocket of space-time that carries it along like a leaf caught on the surface of a wave. It sounds like fantasy. It sounds like something whispered in science fiction novels. But the strange truth is that the idea rests on real physics, real mathematics, real consequences of general relativity. The constraints of the speed of light apply only to objects moving within spacetime, not to spacetime itself. And since spacetime can, under the right circumstances, expand faster than light, there is no rule preventing us from being carried by that expansion. It's not breaking the speed limit. It's stepping outside of it. And, well, the more you sit with this idea, the more it begins to reshape the way you think. Because it's not that the ship outruns light. It's that the ship never actually moves. It stays perfectly still relative to the little bubble of warped space surrounding it. And that bubble, that distortion, does all the motion. It's not thrust, it's not velocity, it's geometry. And the astonishing part is that relativity itself, this very theory that forbids faster than light travel, quietly contains the possibility of a loophole. Not a cheat, not a violation, but a reinterpretation. Because it's not space out there, it's in here, woven through every point in the universe. But before we get carried away, perhaps we should take a moment, breathe, and appreciate what this means. Space is not fixed. It's not rigid. It is more like a fabric, or a sea, or a landscape. And landscapes can be reshaped. Seas can form waves. Fabrics can fold. And, if we could harness that ability, even in the tiniest way, then interstellar travel would no longer require impossible fuel loads or unreachable velocities. It would require something subtler, something that manipulates the structure of reality itself. But you might ask, and you'd be right too, whether this is just theory, whether it exists at all beyond equations scribbled on blackboards. And the answer is, strangely, both simple and profound. The idea of making space move comes directly from general relativity. Einstein himself showed that energy and mass tell spacetime how to curve. The universe has been warping itself since the moment of its birth. We are simply wondering whether that same principle can be applied intentionally. And if the universe can expand faster than light, as it did during cosmic inflation, why not contract too? Why not create a local expansion behind a craft, a local contraction ahead of it, forming a self-contained bubble that moves freely through the cosmic sea? It almost feels as though the universe is whispering a hint. That the trick to crossing great distances is not to accelerate through space-time, but to reshape it so distance itself becomes flexible. But then comes the inevitable question. If the idea is grounded in physics, why hasn't someone built it? Why don't we see prototypes soaring across our skies? And, the answer is bound up in energy. Not energy to accelerate, not energy to push, but energy to warp space itself. Warping spacetime requires exotic forms of energy, densities we have never produced at scale. But the idea gives us something rockets never could: a path, even if distant, toward crossing the stars without violating the cosmic speed limit. And perhaps the most astonishing insight in all of this is that a warp-driven craft doesn't suffer time dilation. Inside the bubble, time flows normally. Clocks tick at the same rhythm. Hearts beat at the same pace. The outside universe may blur in exotic ways, but from within, the journey feels natural. It's not traveling close to the speed of light. It's letting space-time do the moving. Imagine sitting comfortably in your cabin as the universe bends around your ship. No crushing acceleration, no generations passing on Earth while you drift. Instead, you ride spacetime as casually as a surfer rides a wave. It's not just movement, it's movement reimagined. But we must stay grounded. We must acknowledge the difference between possibility and practicality. Because while relativity permits the concept of moving space, it does not tell us how to manufacture the energy needed. It only tells us it is not forbidden. And that is enough for scientists to dream. For in physics, the difference between forbidden and difficult is the difference between impossible and inevitable. It's what separates old fantasies from future technologies. And well, maybe this is where the emotional side comes into play. There is something deeply human about looking at the stars and refusing to accept that they are forever out of reach. Something almost stubborn in our insistence that distance should not define our destiny. A warp bubble, a space-time wave, a bending of the cosmic fabric. It's not just an engineering idea. It's a symbol of our longing. We grow older, clocks tick, civilizations rise and fall, but the stars remain. And perhaps warp travel represents our way of reaching back toward them, of saying that we are not content to stay in our cradle. But let's return to the physics for a moment. When we speak of bending space, we're not talking about deforming a piece of rubber. We're talking about altering the curvature of the universe itself. In Einstein's equations, curvature is shaped by energy and momentum. And if you can manipulate that curvature, you can create regions of expansion and contraction. A bubble, a wave. The ship inside the bubble experiences no acceleration, no stress, no stretching of time, no contraction of length. It simply rests while the universe glides beneath it. And, the idea might sound radical, but the early universe provides proof of concept. During inflation, space-time itself expanded faster than light. Galaxies today are moving away from us faster than light due to the expansion of space. None of this violates relativity. It's merely the universe behaving as the universe always has. So what we are imagining is not unprecedented. It's not science fiction. It's a directed form of something the cosmos already knows how to do. The question is whether we can learn to do it intentionally, whether we can create controlled regions of warped space-time, whether we can understand energy in a deeper way, vacuum fluctuations, quantum fields, exotic densities, to make the impossible routine. And, well, even if the energy requirements seem astronomical now, we must remember that so too did electricity, flight, and space travel in their infancy. Every great leap in human history was preceded by a period where the idea seemed absurd. Perhaps warp travel sits today where powered flight sat 3 centuries ago, a dream unsupported by current materials, current knowledge, current tools. But dreams evolve, understanding deepens, and physics, with its quiet patience, continues to reveal pathways we once thought forbidden. So, as we consider the idea of making space move rather than the ship, we enter a new landscape of possibilities, a landscape where geometry becomes engine, where distance becomes negotiable, where the universe is not a wall, but a field of malleable structure. And, well, this naturally brings us to the next step. If the idea of a warp bubble is possible in principle, what does the mathematics actually look like? What shape does space-time take? What would such a drive require, not just philosophically, but physically? And, that is where we must turn next. To a moment in the late 20th century when a physicist named Miguel Alcubierre sat down and wrote the equations for a warp drive on paper. not fiction, not fantasy. Real equations arising from general relativity itself. A drive that contracts space ahead, expands space behind, and carries a ship inside a perfectly flat region, safe, protected, and free from time dilation. And as we step toward that idea, we begin to see the cosmos not as a prison of distance, but as a canvas waiting to be shaped. And, as we drift from that image of a starship resting gently inside a moving pocket of space-time, the next natural step is to ask how such a thing could even be imagined, mathematically. Because at some point, someone had to sit down, stare at Einstein's field equations, those dense, elegant relations between curvature and energy, and wonder if they could be shaped into a mechanism for travel. And, well, in the early 1990s, a physicist named Miguel Alcubierre did exactly that. It's fascinating, really. Not just that he dared to ask the question, but that he dared to run the equations all the way through. We often imagine breakthroughs appearing in lightning flashes, in moments of pure epiphany. But in reality, they often come from long hours of staring, adjusting, calculating, from asking whether the impossible might simply be the unfamiliar. Alcubierre wasn't trying to build a spaceship. He wasn't sketching engines or drawing blueprints. He was exploring geometry. Exploring the structure of spacetime like an adventurer maps the terrain of an uncharted world. And what he found, what emerged from the mathematics when he pushed and stretched and folded the equations, was a shape, a structure, a solution to Einstein's theory that produced a kind of bubble, a region where space contracted in front and expanded behind. That was the warp bubble. And perhaps the most surprising part was that the interior of the bubble remained completely flat, completely normal. No forces, no distortion, no time dilation. The ship inside would feel as calm as a pebble nestled at the center of a pond, while the water around it ripples outward. But let's slow down, and really picture this. Because the conceptual beauty of the Alcubierre solution lies not in propulsion, but in curvature. Imagine spacetime as a sheet. If you compress the sheet in front of you and stretch it behind, the sheet itself shifts your position. You are not sliding across it. The sheet is carrying you. And relativity, with all its strict rules, does not forbid this. That is the key. The ship remains motionless relative to its local spacetime. It never violates the speed of light locally. And yet, the bubble, the distortion, can move faster than light relative to distant observers because spacetime itself is doing the motion. It's not just clever, it's profoundly elegant. A loophole that exists not because physics is broken, but because physics is richer and more subtle than we first imagined. And, well, Alcubierre's mathematics was crystal clear on this point. The warp bubble requires a ring-like region of curved spacetime, expanding behind and contracting ahead, with the ship resting in the middle. As the bubble moves, the ship goes with it, smoothly, silently, effortlessly. The universe, it seems, can carry you farther and faster than any rocket ever could, if only you know how to ask. But then comes the shadow cast across this dream. Because when Alcubierre calculated the energy requirements for his bubble, the numbers were staggering. Not difficult, not huge, staggering. The energy needed wasn't equivalent to burning fuel or harnessing solar power. It was equivalent to converting the mass of Jupiter entirely into exotic energy. Imagine that for a moment. The entire gravitational bulk of Jupiter, an enormous world of storms and gas and swirling hydrogen, converted into the strange negative energy needed to sustain the bubble's walls. Not to move the ship, not to power it, just to shape spacetime into the necessary configuration. It's not just impractical, it's almost terrifying. It suggests that we are playing with ideas at the very edge of what the universe allows. And yet, the mathematics works. It's not fiction. It's not fantasy. It's a real solution to Einstein's equations. The problem isn't the idea, it's the energy. But perhaps we shouldn't be discouraged. Perhaps we should see this not as a barrier, but as an invitation. Because physics is full of ideas that once required impossible energies until we learned more. Quantum tunneling, nuclear fusion, even electricity, all felt unreachable in their infancy. And, well, the universe does not hide its secrets maliciously. It hides them behind layers of difficulty so that only persistence, curiosity, and humility can peel them open. So let's return to the warp bubble itself. What does it look like mathematically? Alcubierre described spacetime being compressed in front and stretched behind. This creates a gradient, a difference in geometry, that shifts the bubble along like a bead sliding on a thread. And the ship inside sits in a region of pure, flat space-time, completely protected from tidal forces. Inside that bubble, you could float in your cabin, drink coffee, talk with your crew, watch stars shift outside the window. And no matter how fast the bubble travels relative to the universe, time inside flows normally. We grow older. Clocks tick, at the same rhythm as if you were sitting on Earth. It's almost unsettling in its comfort. And, well, the bubble's exterior is where the strangeness occurs. Space in front is squeezed, like pushing down on the fabric. Space behind is pulled, like stretching it apart. And the energy required to create this pattern must have negative density in some regions. Negative energy density. A phrase that feels almost like poetry, but is in truth one of the most exotic concepts in physics, and one we will explore more deeply in the next chapter. But even before we get there, the implications of Alcubierre's model are immense. It means general relativity not only tolerates, but supports the idea of spacetime behaving like a conveyor belt. It means faster-than-light travel is not forbidden by physics, but merely by our limited ability to manipulate energy. It means that impossibility is not absolute. It is conditional. And, this is perhaps why Alcubierre's paper created such a stir. Not because it promised starships in the immediate future, but because it proved, rigorously, mathematically, that our dreams of bending space are grounded in the same physics that govern black holes, gravitational waves, and cosmic expansion. The model revealed another intriguing feature. The bubble is completely insulated from the outside universe. No signal inside can reach past the bubble's walls, and no signal outside can penetrate in. This makes controlling the bubble from the inside problematic. The pilot cannot simply steer. Steering must be built into the bubble's structure from the start. It's like placing yourself in a river current. You don't control the river with your hands. You control it by shaping the channel before you enter. That leads to fascinating engineering puzzles. How do you start the bubble? How do you stop it? How do you steer it? These are not flaws of the mathematics, but consequences of the geometry. And once again, we begin to see that warp travel isn't just propulsion. It's architecture. It's sculpting the universe into a shape that carries you. But let's return to the sheer magnitude of the original energy calculation. The mass of Jupiter converted into exotic energy. It's almost absurd. Yet even absurdity can be a starting point. Over the years, physicists have refined Alcubierre's model, tweaking the bubble's shape, adjusting the geometry, experimenting with alternative metrics. And these refinements have dramatically reduced the energy requirement, though not to anything remotely close to what we can produce today. Still, the trend matters. It shows that the warp bubble is a flexible concept, one that may shrink in difficulty as our understanding deepens. And, this brings us to another profound insight. Alcubierre's model is not the final word. It is the first whisper, a proof of possibility, a demonstration that the laws of physics do not forbid what our stories have dreamed of for centuries, crossing impossible distances in human timescales. It's not just science, it's hope written in equations. So, as we contemplate this early warp drive concept, sitting there in the mathematics like a seed waiting for the right conditions to sprout, we also begin to feel the weight of its challenges. The energy requirement, the need for negative energy, the difficulty of controlling the bubble, the absence of any known material capable of creating such curvature. These challenges do not diminish the idea, they illuminate it. They show us the path ahead, steep and winding, but unmistakable. And well, perhaps this is how all great journeys begin, not with practicality, but with possibility. And as we linger in that thought, gently holding the shape of Alcubierre's bubble in our imagination, the next question emerges with almost inevitable clarity. If the warp drive requires negative energy, then what exactly is negative energy? Does it exist? Can it be produced? Is it something the universe already knows how to make, even if only in tiny, fleeting amounts? These questions form the doorway to the next chapter. The doorway to one of the strangest, most counterintuitive frontiers in physics. And so, as we leave Alcubierre's elegant geometry behind for a moment, we turn toward the deeper mystery at the heart of the warp drive concept. The mystery of exotic matter, negative energy, and the delicate quantum effects that hint, ever so faintly, that the universe might already contain the ingredients we need. And, as we leave behind that shimmering mathematical shell of the Alcubierre bubble, we begin to feel the weight of its most difficult requirement pressing in on us. Because if the warp bubble is the stage, then its fuel, the substance that shapes space-time into that extraordinary configuration, is something far stranger than anything we have ever touched. Negative energy, exotic matter, words that feel as if they belong not to physics textbooks, but to whispered myths. And yet, they arise naturally from the equations. But well, even saying the phrase negative energy makes us pause. Because energy, as we know it, is always positive. Fires burn, stars fuse, photons stream. Every form of energy we experience adds to the universe. It warms, it accelerates, it illuminates. So the idea of energy that pulls instead of pushes, that bends space in the opposite direction, feels almost unsettling. It's not just unfamiliar, it is deeply counterintuitive. We have to remind ourselves that this strangeness isn't a flaw. It's a clue that the warp bubble requires something the cosmos produces only in tiny, fleeting whispers, something that lives in the quantum vacuum, in the restless fluctuations of fields that never stop trembling, even in perfect darkness. Negative energy density. The universe can make it, but only in microscopic amounts and only under very special conditions. And, well, this brings us to the Casimir effect, one of the most delicate and beautiful demonstrations of quantum mechanics at work. Two metal plates placed incredibly close together, closer than a fraction of a hair's width, experience a force pushing them inward. A force with no classical explanation. And the reason, strangely enough, is that the plates restrict the quantum fluctuations between them. Fewer fluctuations means lower energy inside compared to outside. Lower energy. A tiny patch of negative energy density. It's astonishing. So subtle, so fragile, and yet it is real. Measured, verified. The only known phenomenon that produces negative energy in the lab. But here's the problem that echoes through every discussion of warp drives. The Casimir effect generates negative energy on the scale of nanometers. A warp bubble requires negative energy on the scale of meters, or perhaps kilometers. The difference is not small. It is a gulf, a canyon, a leap of billions and billions of orders of magnitude. And, this is where many people quietly sigh and say the dream is impossible. But physics doesn't work in size. It works in principles. And the principle is clear. Negative energy exists, not just in mathematics, not just in imagination. The universe itself produces it. So, the question shifts from, is it possible? To, can it be amplified? Can it be stabilized? Can it be shaped into the ring-like distribution required for the warp bubble? The gap between nanometers and starships is vast, but not logically forbidden. Yet we must approach the idea with humility, because negative energy brings danger too. Too much of it can destabilize spacetime, create wormholes, ripples, even in extreme cases, singularities. The universe seems to ration it carefully, as though aware that too much could unravel its structure. Perhaps this is why exotic matter has never been observed in bulk. Not because it cannot exist, but because the cosmos itself is cautious with it. And perhaps this is why the warp bubble, beautiful as it is, demands an energy source the universe rarely provides in abundance. But the story deepens, because negative energy is not just a quantum curiosity. It appears in theoretical models of black holes, in the Hawking radiation that bleeds from their edges, in the stress-energy tensors of exotic space-time geometries. Whenever the universe twists itself into strange shapes, negative energy is there, a shadow of structure. And, Alcubierre's drive is one such geometry. Not just bending space, but bending it in a way that requires tension. Tension that only exotic matter can create. But let's slow down for a moment. Let's breathe. Let's imagine what exotic matter actually is. It's not antimatter, not dark matter, not something you can scoop into a container. It is a form of energy with negative pressure. It stretches space instead of compressing it. It accelerates expansion instead of resisting it. In a sense, exotic matter behaves more like the dark energy that drives the universe's expansion than like anything familiar. And this connection, this subtle whisper between the warp bubble and the accelerated expansion of the cosmos, may not be coincidence. It may be telling us that the universe itself is capable of generating warp-like effects, just very slowly, and on scales far too grand for us to notice in daily life. And, well, that thought is comforting in a strange way, because it suggests that the warp drive isn't an alien intrusion into physics. It's a reflection of how the universe already behaves, under the right conditions. But we must face the difficulty honestly. The amount of negative energy required to stabilize even a tiny warp bubble is far beyond anything we know how to produce. And even if we could produce it, we don't know how to contain it. It slips through our understanding like water through fingers. So, why do physicists still take the idea seriously? Why hasn't it been dismissed entirely? Because physics is not about what we can do today. It's about what the laws of the universe allow. And the laws allow negative energy. They allow warped space-time. They allow exotic geometries that move faster than light relative to distant galaxies. And if the laws allow something, then it remains within the realm of possibility, even if that possibility lies far beyond the horizon of our current capabilities. But let's return to the Casimir effect again. Two plates, a tiny gap, a pressure difference created by fewer quantum fluctuations. It's so delicate that even a faint vibration or thermal change can disrupt it. And yet, this fragile whisper is the only known foothold we have in the world of exotic energy. And it forces us to confront the scale of the challenge. To go from nanometers to meters is a leap of unimaginable magnitude. The warp bubble would need layers of negative energy thick enough and wide enough to encircle an entire spacecraft. The Casimir plates give us a hint, but only a hint, that such manipulations are possible. And, this leads to one of the biggest conceptual leaps in theoretical physics. The idea that spacetime might have a quantum foam structure at the smallest scales, a granular texture, tiny fluctuations blinking in and out of existence. And within that foam, it's possible that negative energy densities emerge spontaneously, flickering like fireflies in the dark. If we could learn to tap into that foam, even slightly, even indirectly, then the gulf between Casimir nanoscales and Starship meter scales might someday shrink. But that remains a dream, distant, shimmering, but not extinguished. The deeper issue is that negative energy often behaves unstably. It wants to expand. It resists confinement. It pushes rather than pulls. So to shape it into a ring around a warp bubble requires a kind of gravitational artistry we barely understand. And yet, these challenges have not stopped theoretical physicists from exploring every angle. There are models that reduce energy requirements, models that smooth the bubble walls, models that redistribute exotic matter more efficiently, each one a tiny step, each one narrowing the gap between fantasy and possibility. And well, as we explore these refinements, we begin to realize that the warp drive is not one idea, but a family of ideas, a spectrum of possibilities shaped by geometry and energy. The original Alcubierre model is just the first stone in that arch, but the central challenge remains: negative energy, exotic matter, quantum strangeness that sits at the boundary of what is measurable. And, well, perhaps this is why the warp drive continues to enchant us, because it asks us to look not only outward toward distant galaxies, but inward into the quantum fabric of reality itself. It asks whether the universe, in its deepest layers, holds tools we have not yet learned to use. It's not just physics, it's philosophy. The warp drive forces us to confront whether the universe is fundamentally approachable or fundamentally distant, whether the stars are within reach or forever beyond our grasp. And, as we hover in this tension, between the possible and the impossible, we find ourselves looking toward the laboratories where scientists are already experimenting with quantum vacuums, vacuum fluctuations, and the subtle shaping of spacetime curvature. These experiments won't produce warp bubbles. Not today, not tomorrow. But they are steps, small, humble, necessary. Because every great leap begins with the smallest measurable hint. And so, the chapter on exotic matter and negative energy ends not with answers, but with questions. Questions that push us toward the next stage of the warp drive story. If negative energy exists only in tiny amounts, what are researchers doing today to understand it? Are there ways to reduce the energy requirements? Are there new models that move us closer to feasibility? These are not the questions of science fiction. They are the questions of laboratories, theses, and research papers being written in the world right now. And as we turn our gaze toward those studies, toward real progress, however incremental, we step naturally into the next chapter, where physicists working in the quiet corners of spacetime research continue to chip away at the impossible, inch by inch, experiment by experiment, toward a future where perhaps the warp bubble is more than a whisper in equations. And, as we step forward from that quiet frontier of exotic matter and impossible energies, we find ourselves drawn toward something more grounded, more human, toward the real laboratories, the real researchers, the real experiments that, even now, inch us ever so slightly closer to understanding whether warp travel is merely a beautiful mathematical curiosity or the early sketch of a future technology. And well, perhaps the most striking truth is that progress, though slow and subtle, is undeniably happening. You see, long before warp drives captured the collective imagination, a handful of physicists were already exploring the fringes of spacetime manipulation. And one of the most intriguing figures in that story is Dr. Harold White, a quiet, thoughtful engineer who, working with NASA's EagleWorks laboratory, began asking whether Alcubierre's idea, once dismissed as fantastical, could be reshaped into something more feasible. His work in the early 2000s and later refinements in the decade that followed sparked renewed excitement. Because instead of treating the Alcubierre metric as fixed, he treated it as flexible. He asked whether changing the shape of the bubble, its thickness, its density profile, its curvature, might dramatically lower the energy required. And, surprisingly, the calculations showed that it might. Not from Jupiter mass scales down to laboratory energy scales, but enough to shift the conversation from pure impossibility to extreme difficulty. That is not a small shift. In science, a 1,000-fold reduction is enormous. It suggests that geometry isn't rigid. It whispers that we may one day find ways to coax spacetime into more cooperative forms. And, well, White went further. He proposed ring-shaped configurations, toroidal energy distributions, and modified spacetime metrics that reduced energy demands by orders of magnitude. He even began designing small-scale experiments meant to detect minute distortions in spacetime, tiny ripples, tiny bends, tiny signatures that might reveal whether energy can indeed be shaped into warp-like patterns. Some of these experiments used laser interferometry. Some relied on vacuum chambers. Others attempted to create gradients of electromagnetic fields arranged in configurations inspired by Alcubierre's geometry. They were not warp drives, far from it, but they were steps. Gentle, fragile attempts to see whether the fabric of space can be nudged. And, that's the thing. We often imagine breakthroughs arriving suddenly, in brilliant bursts. But in truth, they arrive in whispers. They arrive as subtle measurements on oscilloscopes, as barely perceptible signal shifts, as pages of corrected equations and calibration notes. And those whispers matter because they tell us that spacetime is something we can study, not just admire. Meanwhile, other teams around the world have begun exploring microscopic spacetime distortions using high-precision instruments. Quantum vacuum laboratories, gravitational wave detectors, cryogenic systems designed to isolate the faintest fluctuations. Their work is not tied directly to warp drives, but indirectly it expands our understanding of how energy interacts with spacetime. And expanding that understanding is essential. We still have no direct evidence that controlled spacetime curvature is within reach, but we do have evidence that spacetime responds, that mass bends it, that motion stirs it, that even vacuum fluctuations ripple through it. And so, The idea that one day we might engineer these responses is not entirely unreasonable. Well, one of the most fascinating avenues being pursued involves optimizing the shape of the warp bubble. The more smoothly the curvature changes, the less exotic energy seems to be required. Spiky, abrupt distortions demand enormous energy, but gentle gradients demand less. It's like trying to sculpt a wave, not carve a cliff. And each refinement brings us closer to knowing what is truly feasible. Another thread of research involves trying to measure extraordinarily small variations in the vacuum energy of space. Because if negative energy can be generated, even fleetingly, then perhaps it can be enhanced. Not just by widening the Casimirs, plates, but by stimulating fields, arranging resonant cavities, or exploiting materials that interact with the vacuum more strongly. None of this is easy. None of it is guaranteed. And none of it brings us anywhere close to building a warp-capable vessel in our lifetime. But that isn't the point. The point is that scientific curiosity persists, that researchers continue to push gently at the edges of what is known, that even the smallest experimental hint can inspire new models, new hypotheses, new dreams. And though it may seem trivial, micrometers here, nanometers there, the cumulative effect is profound. It teaches us how space responds to energy. It teaches us how quantum fields behave when constrained. It teaches us that space-time is not a silent void, but an active participant in its own evolution. And, well, even the failures are valuable. Because when an experiment contradicts a prediction, it tells us which mathematical pathways to abandon and which ones to follow. It refines our understanding. It sharpens our intuition. So where does that leave us? Are we any closer to warp travel today than we were decades ago? The honest answer is yes and no. Yes, because our understanding of quantum fields, gravitational curvature, and vacuum energy is orders of magnitude deeper than before. And yes, because we have discovered ways to reduce energy demands, even if only on paper. But also no, because the gap is still vast, still humbling, still a canyon of technological impossibility. But we must remember something essential. It's not the speed at which progress occurs that matters. It's the direction. And the direction is forward. Always forward. Always toward a deeper understanding of space-time and the energies that shape it. And, this sets the stage for a broader question. If the Alcubierre drive is only one possible solution, then might there be others? Other warp geometries? Other ways to fold space-time? Other approaches that might avoid the steepest energy cliffs? That question does not detract from the work being done today. It amplifies it. It reminds us that science is not a single straight path, but a branching forest of possibilities. And as we wander deeper into that forest, we find new models, new geometries that offer promising alternatives. So, as we step gently from the real laboratories and the faint space-time measurements of our world, we turn toward the next chapter, where theorists explore drives that don't rely on the same energy profiles, drives that smooth out the edges of curvature, drives that seek to tame the very instability of warp bubbles themselves. And perhaps in those alternative models, we may find hints, not certainty, not breakthroughs, but hints of a future where the stars feel just a little closer than they do today. And, as we drift from those delicate laboratory experiments, those tiny ripples in space-time measured in microns and nanoseconds, we find ourselves standing before an even wider landscape of ideas. Ideas that stretch beyond Alcubierre's original concept. Ideas born from theorists who asked, almost shyly, whether spacetime might offer more than one pathway toward faster than light travel. And well, this is where alternative warp models begin to appear like constellations in the dark. You see, Alcubierre's solution is elegant, yes, but sharp around the edges. Sudden changes in curvature, regions of extreme tension, energy densities that rise violently at the bubble's boundary. And so, it didn't take long before physicists began asking whether the bubble could be smoothed, softened, made more stable. One of the first to attempt this was José Notario. He proposed a warp drive that doesn't rely on expansion and contraction of spacetime in the same way. Instead of sculpting the fabric by pulling it forward and backward, his model shapes the flow of space itself. And the surprising part is that in Notario's geometry, the bubble's boundaries do not possess the same explosive distortions. Space flows like a river around a stone, not like a cliff face collapsing and rebounding. Not just simpler, but also more stable. That matters, because stability is one of the great obstacles for any warp concept. The bubble must not shear, must not collapse inward, must not generate singularities. And Notario's work, while still deeply theoretical, suggests at least a conceptual path toward gentler curvature. Curvature that requires less exotic matter, though still far more than we can produce. And, well, even if these refinements seem subtle, they reshape the conversation. Because every improvement in geometry lowers the barrier by some fraction. Every smoothing of curvature, every reduction in gradient, brings the idea a microscopic step closer to feasibility. But then, another thread draws our attention away from pure geometry toward something grander: dark energy. The strange, invisible pressure that drives the accelerating expansion of the universe. It is not exotic matter in the warp drive sense, but it is negative pressure. It does stretch space. And what's extraordinary is that dark energy permeates the cosmos, not in laboratories, not in isolated phenomena, but everywhere. So, the universe itself contains a vast reservoir of the very thing we struggle to generate artificially. Not in a usable form, of course, not in concentrated streams or controllable pockets, but as a background pressure, a faint, persistent push that shapes the evolution of galaxies. And well, some theorists have asked whether dark energy might someday be harnessed or redirected, not to create warp bubbles outright, but to influence space-time curvature in subtle ways. Perhaps not a warp engine, but a warp assistance, a gravitational nudge, a field amplifier that nudges space-time where we want it to flow. It's speculative, highly speculative, but it aligns with a deeper truth. The universe already stretches space, already manipulates its own geometry, already performs the very act that warp drives rely upon. The challenge is not persuasion, it is control. And that brings us to an even stranger frontier, one that sits not at the scale of galaxies, but at the smallest structures imaginable, the Planck scale. The scale at which spacetime may not be smooth, but granular, a foam, a jittering mosaic of quantum excitations, a place where geometry flickers, where distance and time exist only probabilistically, where curvature dances like fireflies. We do not know what spacetime looks like there. Not really. String theory suggests vibrating loops. Loop quantum gravity suggests quantized volumes. Other theories propose networks, lattices, or interconnected nodes that form the skeleton of the universe. And if spacetime really is granular, if it has a microscopic structure, then perhaps warp curvature could emerge from manipulating that structure directly. Not sculpting a continuous sheet, but adjusting the granules. Not bending a smooth fabric, but rearranging the underlying threads. And, well, that idea is astonishing, because it implies that warp travel might not be achieved by brute forcing vast energy requirements, but by learning to guide the quantum architecture of space itself, like tuning an instrument rather than pushing a boulder. Still, all of this remains theoretical, speculative, fragile. There is no experiment, no observation, no measuring device that can probe the Planck scale directly. It sits far beyond our reach, shielded by energies so extreme they make even black holes seem gentle. And so we are left with mathematical glimpses, shadows cast through equations. Yet even shadows can guide us. And, as we follow these threads, Notario's gentle warp geometry, dark energies, cosmic pressure, the quantum granularity of spacetime, we begin to understand something quietly profound. Warp travel is not one idea. It is a family of ideas, a landscape of possibilities, all interconnected, all pointing toward the same horizon, motion without motion, distance without distance. But we must remain honest. Every alternative model shares the same ultimate challenge: exotic energy, negative pressure, curvature control mechanisms far beyond our current reach. Whether the geometry is smoothed or the bubble is reimagined, the fundamental requirement persists. It's not that physics prohibits warp travel. It's that physics demands a kind of mastery we have not yet achieved. And yet, we keep looking, we keep refining, we keep dreaming. Because the more we explore these alternative models, the more we realize that the warp drive is not a single, impossible mountain, but a range of peaks. Some taller, some shorter, some hidden behind clouds. And perhaps, someday, one of those peaks may reveal a trail we can actually climb. Well, maybe that is the quiet miracle of theoretical physics, that it allows us to explore landscapes we cannot yet touch, that it allows us to ask bold questions, not just about space-time as it is, but as it might be shaped by future intelligence, future engineering, future insight. And, well, these alternative warp models, though uncertain, prepare us for the final and most human question in this journey. Not the equations, not the metrics, but the reason we pursue these ideas at all. Because beyond the mathematics lies a deeper truth, that warp drive research is not only about reaching the stars, but about reaching a fuller understanding of reality itself. And that truth points us toward the next chapter. So, as we step from the strange geometries of Notario's drive and the whispering pressure of dark energy, we walk naturally into the last part of this journey, where the value of this research, even if warp travel proves forever out of reach, still illuminates the future of our species, our science, and our place in the universe. And, as we step out from the theoretical forests of alternative warp geometries, we find ourselves face to face with a quieter, more human question. Not how warp travel works, not whether it can be built, but why the pursuit itself matters. Because, well, after wandering through equations, through exotic energies and trembling quantum fields, we begin to sense that the real story of warp drive research is not just about engines, it's about us. You see, when we ask whether humanity can travel faster than light, we are not simply asking a technical question. We are asking whether our future reaches beyond the cradle of Earth, whether we are bound to this single world, or whether we can, someday, step gently across the interstellar sea. And, well, even if warp travel is impossible in practice, the journey of trying to understand it reshapes us. It deepens our knowledge of spacetime. It reveals new clues about quantum fields. it forces us to confront the architecture of reality itself. In a sense, the pursuit becomes a mirror, showing us not the limits of physics alone, but the limits of our imagination. Imagine, for a moment, a future in which these studies continue, a future in which each generation pushes the boundary a little further. Refining experiments, discovering new states of matter, measuring the vacuum energy with greater precision. Even if no warp ship ever sails, the technologies and insights gained could ripple outward into medicine, computing, energy, and our fundamental understanding of the cosmos. That is the quiet truth hidden beneath the surface of warp research. Its value lies not only in success, but also in the pursuit. Not just in what it may give us, but in what it may teach us along the way. And there is something beautifully human about that. Our species has always reached beyond what is immediately achievable. We carved boats before we understood the ocean. We built telescopes before we understood the stars. We studied electricity before we knew what to do with it. Progress grows from curiosity, not certainty. So, when scientists explore warp theory, when they question whether negative energy can be stabilized, whether spacetime can be shaped, they are not indulging fantasy. They are continuing a story that began when the first humans looked up into a night sky filled with cold, distant fires and wondered whether those lights were reachable. Well, in that sense, warp research is almost an act of remembering, a way of honoring the ancient human desire to move outward, step by step, from the familiar to the unknown. And yet, there is another layer to this, a philosophical one. Even if warp travel fails, even if the universe remains too rigid, too difficult to bend, the attempt forces us to confront fundamental questions about existence. What is space made of? Does it have a structure? Why does the universe expand? And what role does energy, positive, negative, exotic, play in shaping the destiny of galaxies? Every step toward answering these questions brings us closer to understanding the story we are living in. The universe is not just a place. It is a narrative unfolding across billions of years. And we, fragile beings on a small blue sphere, have the privilege of reading its pages. And warp research, oddly enough, turns those pages faster. It forces us to examine the rules of the cosmos with sharper eyes. Whether it exists at all as a practical technology is secondary to what it reveals about the nature of reality. It's not out there. It's in here. In the mathematics, in the laboratories, in the questions we dare to ask. But let's look outward again, just for a moment. Imagine what it would mean if warp technology did become real one day. Imagine a future where distance no longer defines isolation, where other stars, other worlds, are not unreachable dots, but destinations. Humanity could spread, not in conquest, but in wonder. We could become a species of many skies, many dawns, many homes, and, that possibility, however remote, reshapes our sense of purpose. It reminds us that our story does not have to end here on Earth, that life, fragile and improbable as it is, might one day step beyond the boundaries that physics currently imposes. Not just survival, but continuation. Not just exploration, but participation in the wider cosmic symphony. But even if warp travel never moves beyond equations, its pursuit leaves behind gifts. New mathematical tools, new quantum theories, new insights into vacuum energy. The kind of knowledge that inspires new technologies in unexpected fields, because physics rarely rewards effort in the way we expect. It rewards it in the way the universe allows. We grow older, clocks tick, but our understanding expands. Slowly, quietly, irreversibly. And, this is why warp research remains meaningful, even when the engineering obstacles seem impossible. Because in science, possibility is not a destination. It is a direction, a compass pointing toward deeper truths. So, when we look at the laboratories studying spacetime distortions, when we read the papers refining warp metrics or exploring alternative geometries, we are not witnessing fantasies. We are witnessing humanity doing what it does best, asking questions that stretch the soul. And maybe that is the heart of it. Warp drive research is not only about reaching distant worlds, it is about reaching a deeper version of ourselves, a version that refuses to surrender curiosity, a version that sees the impossibly distant and whispers, "Not yet, but maybe someday." Well, perhaps that is enough. Perhaps that is the true legacy of warp theory. Not a starship, but a mindset. A way of seeing the universe as open, unfinished, and full of paths we have not yet walked. And, as we stand here, in the quiet dawn of 2025, on a planet still learning, still dreaming, still searching, the final thought emerges with gentle clarity. The pursuit of warp travel is not about certainty. It is about wonder. And that sense of wonder, persistent, restless, luminous, is what leads us naturally into the final reflections of this journey, where we gather everything we have learned about light, space, time, and ourselves, and ask what kind of future we choose to build beneath the stars. And, as we draw the final threads of this long journey together, we begin to sense that the true destination was never really the warp drive at all. It was never just about bending space-time, or chasing the impossible, or searching for loopholes hidden between the equations. Well, you see, it was always about something quieter, something deeper. It was about understanding who we are in the face of a universe so vast that even light itself needs tens of thousands of years to cross our home galaxy. Warp travel may not be something we can build in this century. It may not be something any near future can deliver. It might remain forever just beyond our reach. But that does not diminish its importance. Because in asking whether we can outrun light, we are really asking whether our curiosity has limits, whether the boundaries of knowledge are walls or simply horizons. And, well, every step we have taken, through relativity, through exotic matter, through quantum fields, and the geometry of space-time, has revealed that the act of questioning is itself transformative. Even if warp drives never sail, the insights gained along the way push physics forward. They deepen our understanding of energy, of vacuum, of the very structure of existence. They open doors we didn't know were there. We are a species that dreams forward, always forward. And science is the language of those dreams. It does not promise easy answers, nor quick victories, nor final conclusions. But it promises something better, the chance to inch closer to truth, generation by generation. We grow older, clocks tick, and yet our knowledge expands, quietly, beautifully, relentlessly. Perhaps that is why the idea of warp travel resonates so deeply with us, not just because it could take us to other stars, but because it reflects our desire to refuse stagnation, to keep moving, not just across space, but across understanding itself. It's not merely a technology. It is a symbol, a reminder that the universe is not a closed book, but a living manuscript still being written. So, Even if the Alcubierre bubble never forms around a starship, and even if negative energy forever teases us from the edges of quantum uncertainty, the pursuit remains worthwhile, because it strengthens the very spirit that drives science forward. The spirit that says, explore, question, imagine, reach, and well, when future generations look back, whether standing on Earth or some far-off world, they may see that the true achievement of our time was not building a faster-than-light engine, but daring to ask whether it could exist at all. Daring to look at the stars not with resignation, but with hope. The universe is vast. The universe is beautiful. The universe is patient. And we continue to study it, not because it is easy, but because it is part of who we are. A species born under the night sky, forever lifting its eyes toward distant suns, forever wondering what lies beyond. And perhaps in that quiet wonder, we find the real warp drive, not a machine, but a mindset. The engine of curiosity, the spacetime of imagination, the expansion of knowledge that carries us, gently but surely, toward futures we cannot yet name. And so, this journey ends the way all scientific journeys end, not with closure, but with a deeper invitation to keep asking, to keep exploring, to keep listening to the universe as it whispers its ancient truths. Because in the end, we do not chase the stars merely to reach them. We chase them to understand ourselves.